Hi everyone. This video is all about conditional probability. So suppose you had a situation where you're at work and your workplace says we expect every year 10% of our employees will leave the company. So now suppose you're considering the case of two people, and person one has two options. They can either leave or they don't leave. And person two has two options. They can either leave or don't leave. And then let's just say that event A is person one leaves the company. And event B is person two leaves the company. How would you draw this? Well, what you can do is you can draw a Venn diagram to illustrate what's happening here. You have event A, and then you have event B. Everything in event A represents the outcome that person A leaves the company. Everything in event B represents the outcome that person B leaves the company. Everything in the middle represents the outcome that they both leave the company, given this 10% leaving rate. And everything in C represents this following outcome. C is equal to 1 minus the probability of A plus the probability of B minus probability of A intersect B, or A and B. And this intersect is right here. This is the probability of A and B, both people leaving the company. And as you can see, or as you can think of it as, if you're considering the probability A first, so I'm highlighting blue, then you're considering the probability of B second, which I'm highlighting in orange. The green represents the double highlighted part. So if you just add them, add A and B together, in this case, you are double counting the middle. So you have to not double count the middle to appropriately add this together. And then you're doing 1 minus this because the whole box represents 100% of the choices. So that 1 stands in for 100. And then if you minus that from what is called sort of the union of this, then you get what C is, which is outside of these two circles. So what does this have to do with conditional probability? Well, And I'm going to just call this tab intro so that we correctly label it, obviously. Anyway, what does that have to do with conditional probability? Well, what conditional probability is suppose you already know the outcome of one of these events. So I'll carry this over to the next tab. Suppose you know that the person involved in event A, and we're assuming that each event is an individual person. So suppose event A is person one, and you know that they leave. What is the probability of event B? And it's represented by this formula. The probability of event B given A has already occurred is equal to the probability of A and B occurring, both people leaving the company, over the probability of B. This is conditional probability. This is conditional. It's conditioned on the thing you already know happens. And actually, I need to change this. This needs to be an A to be correct with my example. All right, let's take it from here. What is really going on here? Well, if you do the same graph, and I'm just going to copy the graph from before. And you know, by definition, that A has occurred. You know it's occurred. So by definition, you know that this whole circle has already occurred. Event A is always person one leaves. That's how we've defined the event in this scenario. Well, what conditional probability means is you know that A has occurred, so you've highlighted all of A. What is the probability of B given that A occurs? Well, the only place that probability of B could occur then is in the center right here, because that's the only place that the probability of B actually occurs when A also occurs. Now, I want you to notice something else in this. We've highlighted sort of two circles. Circle one, which is this whole A, and then a semicircle right here. Circle two. Two circles. Notice by highlighting both of them, we are double counting what's in the center again. So we need some way to account for what's in the center so that we still have sort of that portion of probability A and that portion of probability B, but we don't have that portion of probability B. We need to somehow fix this double counting thing. So what ends up happening is by dividing, what you're sort of doing is you're sort of, in a sense, fixing that double counting thing. You're taking the portion of A out of what's in this intersection. So that's the theory behind conditional probability. And you can take it to other examples. So if you've ever seen the TV show Deal or No Deal, the host will offer a bunch of doors to contestants on that show and tell them sort of actually the host what the host will do is the host will open one of the doors first and give them the option to buy what's in the door with whatever the game is playing with. If the person doesn't want it, there's a risk. The host opens another person's door and you get a zoink, which means no prize. And so, you might want to know what's the probability that you get a prize if you skip the first offer and go to the next offer. The same kind of idea. This idea that what has already happened affects sort of what the likelihood of your next thing. Now, there's a couple concepts that are spurned off of this. The first concept is called the multiplication rule. And I'm just going to copy this again and change the tab header. And what this concept is essentially you're taking this probability of A and moving it up to here by using algebra. So you're multiplying by probability of A so that it cancels out on this right-hand side. And you're doing the same over here. This arrow is multiplying by the probability of A. What you get is probability of A times the probability of B given A equals the probability of those two events occurring together. The probability of A and the probability of B. This is a form of combining things together. But this formula only works if you have something, a set of events that are not independent of each other. Meaning, let me give you an example. Meaning, with attrition, from the workplace, and you have two workers, it's possible that one worker talks to the other worker, gossips about work or whatever, and convinces that other worker to leave. And so the likelihood that the first worker leaves is directly related to the likelihood the second worker leaves. In this case, these two events are not independent. One affects the other. So what you would have to do to look at a situation like that is if you wanted to find the probability of both occurring, you'd have to consider the first person's effect on the likelihood the second person leaves as well. And this is not something that you have to go into crazy theories about. Most situations will be fairly obvious if two events are independent or not. Most of the stats questions you'll get kind of assumes this, but understand just that you would use this to sort of add up the probability of two events if they're not independent. Now, if they are independent, let's just say that the probability that someone leaves is not affected by the probability of someone else leaving. So this is your work. Your work is actually a great place to work and stuff like that. So maybe the reason why people aren't leaving your work is because of they're just going off to bigger and better fields. This is then how you combine independent events. And it's because precisely that your B is not influenced by your A. People are leaving work not because they're convincing each other to leave work. They're leaving work for other reasons, going off to bigger, better, brighter futures. So what ends up happening here then is that if you ever want to combine independent events, you use this math. If you ever want to not combine events that are not independent, and often you can easily sort of get that from the problem, or the problem will be clear in this, you use this method. Now, one thing does occur with this, independence often gets confused by something called mutually exclusive. So what mutually exclusive events are, let's consider a different situation. Let's consider voting. So let's say the likelihood that any person will vote for Donald Trump is 61%, and the likelihood that any person will vote for Joe Biden is 39%. I know this is politics, don't hold me over grill here. Um, I'm just making up these numbers off the top of my head. But at the same time, this is a possible situation that could occur in the real world. And so, how you would draw this is let's just say, actually, let's make this first event here T, or a likelihood to vote for Trump, and the second event B, or a likelihood to vote Biden. So if you had a situation where you were at the polls, a person cannot vote for both Trump and Biden. So there's no shared space in the middle. And whenever there's no shared space in the middle, it's called mutually exclusive. There's no shared data points. So it becomes mutually exclusive. And that's the difference. These two events are still independent. You would surmise that how I vote is not going to influence how you vote. But they're mutually exclusive because you can't vote for both. You can't be a Biden supporter and a Trump supporter. It just doesn't work because you only have one vote every presidential election. So the way you combine these events is differently. Unlike multiplication, which is coming from this conditional probability rule, it's sort of saying if you want to add up two events that are independent, you have to multiply them. If they're mutually exclusive, this is different. Remember when we started here and we said that if you wanted to do the complement, you add up what's inside the circles. So it's all of A, all of B, and remove the double counting. Well, notice how in mutually exclusive, there's no middle. So how you would add these events up, probability of T plus the probability of B. And you get the probability of sort of both of them. You've added them up, so the probability of A intersect B would be a way to put that. A and B. Now, why do you even care about this stuff? Why is it at all important to your well-being? Well, In some questions of the book, in your stats classes, and in some questions you might encounter, you may come across something called the distribution of the proportion, or you may even come across something called the binomial distribution. And so I'm going to start with the binomial distribution and showing you how this connects. And then I'm going to continue on with the distribution of the proportion. So a binomial experiment, what it is you only have two choices. It's like, do you leave or not leave? My first example here. So there's a connection already. And you would have learned through, your teachers, your textbook, whatever you have stats for, that the binomial distribution has a formula for variance. And what that formula is n times p times 1 minus p. P is your probability of success. 1 minus p is the probability of failure. So what's happening in this variance formula when you see it is these two probabilities together, the likelihood of success and the likelihood of failure, are being added together because they're independent. The probability of success times the probability of failure is equal to the sum, the probability of success and failure. And so you can think of this as adding together sort of both possible occurrences. And then the n just tells you, it's a multiplier. It just tells you how many number of occurrences have occurred. So across all the occurrences that occurred, this is the spread of probabilities between success and failure. And that's sort of why it's called the variance for the binomial distribution. And it makes sense why these are considered multiplication and independent events. Because if you think about it, when you choose to leave a company, you either have one of two choices. You can either leave or not leave. The fact that you leave is not going to affect the fact that you don't leave, and the fact that you don't leave is not going to affect the fact you leave. The only way that works, the only reason why these might not be independent is if you're considering events as two different persons' choices. But if you're just the first trial by itself, you either leave or you don't leave. You can only make one choice. The fact that you make a choice is not going to affect whether you don't leave, whether the trial is a failure or not. So that's why this is independent. That's why you use multiplication to add them together. And that's why you don't need a conditional probability to add them together. And so that's one connection point for why this is important. Let's give you another connection point for why this is important. This is distribution of the proportion. A lot of you, if you've encountered this in your studies, probably saw a crazy equation and just sort of assumed, oh, I got to deal with it and memorize this and just sort of forgot about it afterwards. That crazy equation was for the standard error of the proportion means, and it was p times 1 minus p over n. What's happening here? It's the same thing that's happening in this multiplication rule. You're assuming that P is your sort of success. I left the company, if that's how you define success. And 1 minus P is your failure. I didn't leave the company. So when you multiply them together, this top part becomes the probability of success and failure. In this case, both the probabilities of you leaving the company and not leaving the company combined. When you divide it by n, it's just essentially taking the average. So in turn, this becomes out of all possible proportions. What's the average probability across both of the probabilities? And then taking the square root gives you the standard deviation across all the different proportions that exist in the problem.